Thermal stress. Thermal stress. We have to define thermal stress. Thermal stress is a stress. Thermal stress is a stress which is set up in a solid rod, which is set up in a rod when the rod is rigidly fixed at its two ends. Thermal stress is a stress which is set up in a rod when the rod is rigidly fixed at its two ends. And its temperature is changed. Hence, thermal stress is a stress which is set up in a rod where the rod is rigidly fixed at its two ends and the temperature is changed. This is a rod. This is a straight rod. An initial length of the rod is L1 at the initial temperature theta 1 degree Celsius. This is a straight rod whose initial length is L1. L1 is the initial length of the rod at initial temperature theta 1 degree Celsius. L1 is the initial length of the rod. At the initial temperature theta 1 degree C. Theta 1 degree C is the initial temperature of the straight rod whose two ends are rigidly fixed at two vertical walls. And these are the two vertical walls. These are the two rigid vertical walls. To which two ends of the rod are rigidly fixed. These are the two vertical rods to which two ends of the rod are rigidly fixed. This is another rigid vertical wall. And in this case, the temperature of the rod is increased from theta 1 degree C to theta 2 degree C. Temperature of the rod is increased from theta 1 degree C to theta 2 degree C. And the rod will bend due to increase in temperature. In this case, the rod will bend and will take this type of shape. This will be the final state of the rod, that is, the rod will bend due to increase in temperature and length increases. Length of the rod also increases due to increase in temperature. This is the rod in final state in which the rod bends due to increase in temperature. The rod bends due to increase in temperature. Final length of the rod increases to L2. This is the final length. L2 is the final length of the rod. And in this case, deforming force, a tension T that is numerically equal to deforming force will act at its fixed ends. There will be deforming force which will be acting at the fixed ends of the rod at theta 2 degree C. Here the tension T is numerically equal to the deforming force. Let L1 be the initial length of the rod at the initial temperature theta 1 degree C. L1 be the initial length of the rod. L1 be the initial length of the rod whose two ends are fixed, whose two ends are fixed, whose two ends of are rigidly fixed to the two vertical walls. L1 be the initial length of the rod whose two ends are rigidly fixed at the two vertical walls, and L1 be the initial length of the rod at the initial temperature theta 1 degree C, theta 1 degree C. Now the temperature of the rod, is increased. Temperature of the rod is increased from theta 1 degree C to theta 2 degree C. Temperature of the rod is increased from theta 1 degree C to final temperature theta 2 degree C. And in this case, length of the rod will increase to L2 from L1. The length of the rod increases to L2. L2 is the final length of the rod at final temperature theta 2 degree C. As the temperature of the rod whose two ends are fixed, are rigidly fixed, as the temperature of the rod whose two ends are rigidly fixed, is increased from theta 1 degree C to theta 2 degree C, a deforming force under bracket F acts at its two fixed ends. A deforming force F acts at its two fixed ends, and the thermal stress set up in the rod, is given by F by A, that is deforming force divided by initial area of cross section. F by A will be what? Where Young's modulus of the solid rod under bracket Y is equal to normal stress, that is F by A divided by longitudinal strain, which is delta L by L1. That will be equal to product of deforming force into initial length F L1 divided by A into delta L. Where delta L is the change in length, and the deforming force, the expression of deforming force F will be Young's modulus Y into area of cross section A into delta L divided by L1. That is the expression of deforming force. And we get the expression of thermal stress as what? F by A will be what? Putting the expression of F by A, or deforming force, we know the expression of deforming force F as equal YA delta L by L1, and putting this expression in the numerator, we get, putting the expression of F, we get YA delta L by L1, YA delta L divided by L1. YA delta L by L1 whole divided by A, that is the expression of thermal stress F by A. Or comma F by A, which is the thermal stress, which will be equal to 1 by A into YA delta L by L1, where delta L is the increase in length of the rod, that is delta L is equal to L2 minus L1. Therefore, the expression of thermal stress, that is F by A, will be Y delta L by L1. Area of cross section A and A will cancel out, that is Y delta L by L1. Y delta L by L1, where delta L is the change in length or increase in length, and L1 is the initial length of the rod. F by A is equal to Y delta L by L1, which is the expression of thermal stress set up in the rod, where change in length or increase in length of the rod, under bracket The change in length of the rod under bracket delta L equal L2 minus L1. L2 minus L1, where L2 is the final length of the rod at the final temperature theta 2 degrees C, and L1 was the initial length of the rod at the initial temperature theta 1 degree C. Now the temperature coefficient, temperature coefficient of linear expansion of the solid rod, temperature coefficient of linear expansion of the solid rod, linear expansion of the rod is given by alpha is equal temperature coefficient of linear expansion, alpha is equal change in length of the rod divided by initial length of the rod into change in temperature of the rod. Therefore, alpha equal to delta L divided by L1 delta theta. That means alpha is equal to delta L divided by L1 delta theta. That is the temperature coefficient of linear expansion of the rod. Now in the diagram, L1 is the initial length of the rod at the temperature theta 1 degree C, and L2, and in this case temperature is increased from theta 1 to theta 2 degree C, and length increases to L2. Alpha equal to delta L divided by L1 delta theta, where delta L is equal to L2 minus L1, which is change in length, and delta theta is change in temperature, that is equal to theta 2 minus theta 1 degree Celsius. Here alpha is equal to delta L divided by L1 delta theta, and delta L is equal to L2 minus L1, which is increase in length or change in length of the rod due to change in temperature. Delta L equal L2 minus L1, which is change in length of the rod due to change in temperature. Or comma alpha L1 delta theta is equal to delta L, which is the change in length. Therefore, delta L equal L1 alpha delta theta, where delta theta is change in temperature and delta L is change in length of the rod. Delta L is equal to L1 alpha delta theta. Delta L is equal to L1 alpha delta theta, which is the change in length of the rod, due to change in temperature. Delta L is equal to L1 alpha delta theta, which is the change in length of the rod due to change in temperature. Therefore, thermal stress F by A had the equation Y delta L by L1, where Y is the Young's modulus, or comma F by A will be what? Y by L1 into, putting the expression of delta L, we get L1 alpha delta theta. So therefore, F by A equal Y alpha delta theta. F by A is equal to Y alpha delta theta. Therefore, F by A equal Y alpha delta theta, where Y is the Young's modulus of the rod, alpha is temperature coefficient of linear expansion, and delta theta is the change in temperature of the rod. F by A equal Y alpha delta theta, which is the thermal stress set up in the rod, due to change in temperature. F by A is equal to Y alpha delta theta, which is the thermal stress set up in the rod due to change in temperature. Therefore, thermal stress is equal to the product of the product of Young's modulus, temperature coefficient of linear expansion, and change in temperature. That means thermal stress is equal to Young's modulus into temperature coefficient into change in temperature. Thermal stress is numerically equal to to Young's modulus into temperature coefficient of linear expansion. Temperature coefficient of linear expansion into change in temperature. So thermal stress is the product of three physical quantities, that is Young's modulus, temperature coefficient. Thermal stress is equal to Young's modulus into temperature coefficient of linear expansion and into change in temperature. So thermal stress is F by A, Y is Young's modulus, alpha is temperature coefficient, and delta theta is the change in temperature of the rod, Now we can compare the expression of thermal stress set up in a rod due to change in temperature and thermal stress or change in pressure in a gas due to change in temperature. Left hand side, thermal stress set up in a solid rod due to change in temperature. On the right hand side, we can write what thermal stress or change in temperature, thermal stress or change in temperature or change in pressure. It should be thermal stress or change in pressure in a gas, thermal stress or change in pressure of a gas, change in pressure acting in a gas due to change in temperature. On the left hand side, we can write thermal stress as F by A. F by A is the thermal stress which is equal to Young's modulus Y, temperature coefficient alpha and change in temperature delta theta. F by A equal Y alpha delta theta. On the right hand side, we can write down the expression of change in pressure of a gas. Change in pressure is delta P, which will be equal to product between bulk modulus K, gamma and delta theta. Delta P is equal to K gamma delta theta, which is the change in pressure, which is the expression of change in pressure of a gas due to change in temperature. Delta P is equal to K gamma delta theta, where K is bulk modulus, gamma is temperature coefficient of volume expansion of the gas, and delta theta is change in temperature. Delta P is equal to K gamma delta theta, which is the change in pressure of a gas, or thermal stress acting in the gas. And F by A on the left hand side, F by A is equal to Y alpha delta theta, which is the thermal stress set up in a solid rod due to change in temperature, where F is the deforming force, A is the area of cross section, and Y is the Young's modulus. Y is Young's modulus of the solid rod. Y is Young's modulus of the solid rod. Young's modulus on the right hand side, where we can write K is the bulk modulus. It is also denoted by capital B. K is the bulk modulus of the gas, and here Y is the Young's modulus of the solid rod. Alpha is the temperature coefficient of linear expansion of the rod. Alpha is the temperature coefficient of the linear expansion of the solid rod. Where gamma is the temperature coefficient. Gamma is also the temperature coefficient of volume expansion of the gas. Gamma is the temperature coefficient of volume expansion of the gas. And what about delta theta? Delta theta is the change in temperature of the solid rod or change in temperature of the gas. Delta theta is the change in temperature. And now we can write down the relation between gamma and alpha. F by A is the thermal stress, which is equal to Young's modulus Y, alpha and delta theta. And delta P is change in pressure, which is numerically equal to the product between K, gamma and delta theta. Now we can write down the expression of temperature coefficient of linear expansion, that is alpha equal to L2 minus L1 divided by L1 under bracket theta 2 minus theta 1. Alpha is equal to L2 minus L1 divided by L1 under bracket theta 2 minus theta 1. That is the expression of linear expansion of temperature coefficient of linear expansion of solid, where delta theta is equal to theta 2 minus theta 1 degree C, or theta 2 minus theta 1 Kelvin, where gamma is equal to, that is the temperature coefficient of volume expansion, gamma is equal to V2 minus V1 divided by V1 into theta 2 minus theta 1. Gamma is equal to V2 minus V1 divided by V1 theta 2 minus theta 1. And also gamma is equal to 3 times of alpha, gamma equal to 3 alpha. Gamma is equal to 3 alpha, where V2 and V1 are the final and initial volume of the gas. That means gamma is equal to V2 minus V1 divided by V1 under bracket theta 2 minus theta 1. That is the expression of temperature coefficient of volume expansion of the gas.